Hi. So I'm sure everyone is enjoying what seems to be the end of the COVID pandemic. People are getting the vaccine and things are returning back to normal. But I want to take you back to the beginning of the pandemic, April 7th, 2020 to be exact. See, this is when Riot Games' new first-person shooter Valorant came out. And for me, this meant, well, for lack of a better term, I was king. I fell in love with this game, and it intrigued me enough to want to try to investigate what is the gravity in Valorant. It's definitely not because if I don't do this extra credit project, I may fail a course. So to start, we need to figure out exactly how we can do this. Well, as a mechanical engineering student pursuing a physics minor, this shouldn't be that difficult, right?
Gravity is just the downward force exerted on objects by the planet they are on. On Earth, the force of gravity is 9.8 meters per second squared. On other planets, and in this case games, there's a different magnitude. Thankfully, a bunch of nerds already found a way to calculate things like gravity. Since gravity is just downward acceleration, we can use the magical kinematics equations. Don't ask why they work, because I don't know. But using the change of position is equal to initial velocity multiplied by time plus 1/2 acceleration multiplied by time squared, we can find gravity. We're just going to need to find distance, initial velocity, and time. The best way to do this is to jump off a cliff. No, seriously, we're going to fall. In Valorant, there are a lot of things to jump off. If we can figure out the height we are jumping from, the time it takes to fall, and the initial velocity when falling, we can solve for acceleration, which would be gravity. Now with the previously determined equation, we can make everything in just the y direction. Now our distance is the change in height, essentially the height we are jumping from. In Valorant, there's a ping system that measures a distance from you to the thing you ping. I know it's hard to see, but in this picture you can see that it measures 8 meters. We could choose a height, and using the stopwatch app, we could record the time to 3 decimals. Since we are falling, there's no initial velocity. Now we're just left with algebraic manipulation, and if you do that, we have the gravity is equal to 2 times the distance divided by time squared. So, we just need to record ourselves jumping, and it's going to look like this. Okay, I messed up here, but after enabling cheats, we won't die to fall damage. So I decided to jump in 2 different places, one at 8 meters and one at 5 meters. Doing 5 trials of that, from that data, we get that gravity is around 40 meters per second squared. Yeah, we're not done. This number is huge. It's over 4 times the gravity on Earth. It doesn't really make sense for the developers to make it that way when it's supposed to be a somewhat realistic game. Clearly we have some errors here. First, it would be easier with more data, so I got my friend Bonzi to help me. I had him jump off the same 2 spots, but I had a better view, making it easier for me to time his jumps. Nice, but our data is only slightly better. Next, we have to account for my reaction time. Since I'm only a human, it's really hard to see when the player model actually starts falling and when it hits the ground. Along with that, the recording is only in 60 frames per second, so the player model is hitting the ground at a different time than I actually see it happen. We have to account for this human and technological error. So I used Googly and did a reaction time test from the human benchmark to see that I had 245 millisecond reaction time. Adding that to our original values from time gives us an adjusted time value. Now I know I technically have 2 reaction times, one when the player starts falling and then hits the floor. This should cancel each other out. But in reality, it's a lot easier for me to see when the player hits the ground than when the player starts falling. So adding this time should help to account for both the human and technological error. So we're good now, right? No. The height doesn't quite make sense. The measurement that the game gives me is the distance from my in-game eyes to the floor. But when I'm timing this, I'm timing really the time it takes for my feet to go from the distance to the floor. So now we have to change the height to account for that. Oh boy. It's actually really hard to figure this out because I don't know the height of my in-game player model. But thankfully, there's a specific box in the game with dimensions. Kind of. The box is a volume of 32.5 cubic meters. From there, we can start. We can do pixel measurements to find out exactly how much bigger the length is compared to the width and height, and from there we can find the volume. We can see that the length of the container is 767 pixels and the width is 331, meaning the length is 2.973 times bigger than the width. Here we can work out a way to find the exact dimensions of the container. Since the front of the container is a near perfect square, we're going to treat it as such and say that that part is 331 pixels by 331 pixels. So now what we're saying basically is the length is 2.973 times bigger than both the width and the height. Meaning, if length times width times height equals volume, then a squared times a times 2.973 equals 32.5. After doing some math and solving this equation for a, we learned that our container is 2.219 meters tall, 2.219 meters wide, and 6.598 meters long. Now if we examine the height of a character in-game, we can figure out what their height is in meters. In Valorant, all characters are the same height, so it doesn't matter which one we use. In this case, we use character Cypher, who measures at 169 pixels tall. Using a ratio of pixels to height, we can figure out exactly how tall these models are in meters. So after solving this ratio for B, we can figure out that the models are 1.133 meters tall. Subtracting our initial height by the height of our models gives us a more accurate change in position. So now that we account for human error and the issues with our height, we can throw all the data into an Excel sheet and bada bing, bada boom, we have our results. Our first trial gives 17.0 meters per second squared, and our second gives 13.6 meters per second squared. Both of these were done in the first person. For trial 3, we get 15.6 meters per second squared, and for trial 4, 15.3 meters per second squared. These two were done in the third person. To make this more accurate, we're going to drop the highest and lowest values of gravity from each individual trial and take their average. For example, in trial 1, we remove the highest gravity value of 18.0 and the lowest gravity value of 15.8, and then take the average of the remaining three values. If you do that and then average the first two trials with the second two trials, you would get that they're both equal to 15.3 meters per second squared. And then if you average those trials, you get that we have 15.3 meters per second squared over all four trials. So to conclude, the gravity in Valorant is approximately 15.3 meters per second squared.